The landscape of surface mines, such as quarries, changes frequently. Mining involves blasting, drilling, crushing, screening, and heavy earth movement in the orders of tons of earth material. Efficient planning of operations, such as routing of roads, determination of stockpiles, and so on, requires an accurate terrain model. Hence, mining involves frequent update of the terrain model. Traditional methods of surveying using total stations for updating the terrain often are time-taking and unsafe. To solve this problem, LiDAR scanning from UAVs are increasingly used. LiDAR scanning from UAV offers an accurate result and a faster turnaround time. With LiDAR scanner, every bump and cranny of the quarry can be accurately mapped. It's also a safe way to scan the often unstable and rough terrain of surface mines. Once the data collection stage is completed, the LiDAR data needs to be processed. LiDAR data processing with ERDAS Imagine is pretty intuitive. ERDAS Imagine offers solutions for the generation of surface models, cross-section profiles, contour generation, and various terrain analysis options, including slope analysis, distance measurements, and identification and computation of volume changes. Results are generated often within minutes after data collection, making it possible to extract timely, actionable information as frequently as needed. In this demo, we'll showcase how ERDAS Imagine can be used to identify and compute stockpile volume changes from two LiDAR scans that are collected 2 years apart. Let's display the LiDAR data side by side and first do a visual inspection. The data on the left is the baseline data, and the one in the right is a recent scan. Some of the changes are easily identifiable. I'll load a shapefile which highlights areas of significant terrain changes between the two datasets. This shapefile is generated using ERDAS Imagine. We'll see how it's generated later on. We can also view the LiDAR data in 3D views, which should make the visual identification easier. Look for the areas highlighted by the shapefile in the 2D views. The change identification and volume computation is done using the spatial modeler capability of ERDAS Imagine by bringing together several LiDAR, raster, and vector operators. The inputs for the model are the LiDAR data from the two dates and the quarry boundary. The model has two submodels. The first submodel identifies areas of significant changes in the quarry. As you can imagine, there will be some type of change almost everywhere inside the quarry. In this submodel, we first identify all changes and filter out those that we think are not significant. The filtering can be done either by footprint area or by volume. Let's look at the second submodel. In this submodel, the footprints of each of the areas that are identified as significant changes are buffered by a certain amount and smoothed. These two submodels together eliminate the time-consuming task of visually identifying changes and manually digitizing boundaries. Once the boundaries are automatically extracted, the volume change inside each boundary is computed using the compute volume operator. If the area has material removed from a section of it and added to another section, these are separately accounted for and computed. Let's look at the results. The shapefile you are seeing in the left shows areas that have changes. There are thousands of them. As mentioned earlier, we selected those areas we think have significant changes based on the footprint size. The middle view shows those areas that have significant changes. The rightmost view shows a shapefile with a computed volume change in a table at the bottom of the views. As you see in the table, cuts and fills are separately computed and reported for each area. To summarize, Quarry operation and management requires frequent update of terrain data to generate various metrics. Quarry operators are looking for solutions that enables them to do this accurately and efficiently. One of the frequently computed and reported metrics is volume change, and we saw how this can be done accurately using ERDAS images.